clicking.
And also they do not write on that side, the corner. Usually. I'm just saying.
There is a recording of last year, so it's okay.
Okay.
All right. So, okay, I hope that you guys who are sitting there can see this. It's written entropy of an ideal gas. This is an S, and this is a Y, not a G. So what I wanted to show you is give you a thermodynamic derivation of a formula for the entropy for an ideal gas that will look pretty similar to something we will derive later on, or we will conjecture later on, which is the formula for the entropy of Boltzmann. So let's start with an exercise. The exercise is the following. We have an ideal gas that is sitting inside a volume VI, and we make a free expansion up to VF, and we ask ourselves, what is the change in entropy? Delta S. So delta S is equal to integral VI VF ds.
Marisa,
Yes?
is there an exchange with the environment or something?
No, it's let's say it's thermally isolated. All right. So, and then this is integral VI VF dV ds dV at constant temperature. Okay? Actually, it's not thermally isolated. If I do it at constant temperature, then I have to keep it coupled to a bath where temperature is fixed, right?
Yeah.
Otherwise, it would be constant entropy, not temperature. All right. So now, how do I compute this dsdv? Well, F is so. This is a situation in which the temperature is constant, the volume is changing, and the number of particles is fixed. So temperature is constant, volume is changing, number of particles is fixed. So what kind of thermodynamic potential would we use?
Helmholtz.
Helmholtz free energy. Helmholtz free energy, correct. So which is E minus Ts. And in particular, what I know is that dF is minus S dt minus dV, and therefore S is equal to minus dF dt, and E is equal to minus dF dV. Okay, so now you look at this. So you understand what I want to calculate? You understand that since I'm using T, V, and N as free variables, I have to use the free energy, the Helmholtz free energy as my thermodynamic potential. Now I need ds dV, right? So how do you compute ds dV?
Yeah, the exchange, that would be dV.
How are they called? Maxwell relations, right? So I use the Maxwell relations. The cross derivatives of these two guys have to be equal, and therefore ds dV has to be equal to dP dt. Exactly. So from this follows that ds dV is equal to dP dt. You see how useful it is? It's very simple to use. So therefore this is equal to the integral Vi Vf dV dP dt, right? And now dP dt I know how to compute it. I just use the equation of state. P times V equal to N times R times T. Right? So this is equal to integral Vi Vf of dV over V n times R. Right? And therefore, it is equal to n times R times the log of Vf over Vf. So this is the final formula. Right? So what we learned from this simple exercise is how to use what we discussed last time at the end. These ideas that essentially, I mean, the whole idea of using thermodynamic potentials to describe various situations in which you fix certain variables, and then using cross relations to compute the derivatives that by themselves are not that straightforward to compute, because the SDV, well, you want to compute S, you don't know how S looks like, and here you should compute the SDV. Well, luckily you have the Maxwell relation, otherwise it would not be that easy, right? Even if you know the equation of state. Okay, so let's now try, before getting to the entropy, another interesting exercise, because I want to show you what is the interpretation of derivatives of the entropy with respect to internal energy. And the exercise is the following. So I have two boxes in which I have a certain internal energy, well, a certain volume, and a certain number of particles. Certain internal energy here, a certain volume, and a certain number of particles. And the particles can be exchanged, and the internal energy can be transferred between the two. The entire system is closed. Okay?
Yeah.
So there is a microcanonical or adiabatic or whatever situation. So what is the thermodynamic potential I use to describe this situation? The entire system.
No. Almost free energy.
What? No, it's closed. There is no exchange of heat with the external environment.
Yeah, I think the one we use, internal energy.
Internal energy, exactly. The first one we introduced, internal energy. So we know that E is equal to P ds minus P dV plus mu dN, right? And therefore that ds is equal to dE over T plus P over T dV minus mu over T dN, which therefore implies that ds dE is equal to 1 over T, ds dV is equal to P over T, and ds dN is equal to minus mu over T. Right?
We just stick to using E or U.
Well, this time is E.
Okay.
So E is equal to U today, right? E is equal to U. So let's write it here. So it's the internal energy. All right, so now the question is, I have this situation, E and E2 and E1 can fluctuate, N1 and N2 can fluctuate, etc., etc. And now I ask myself, what is the condition of thermal equilibrium in this situation? So how do I identify thermal equilibrium? Well, thermal equilibrium is a situation in this system in which the entropy is not changing anymore, right? It's the minimum is a, right. But make a transformation in which the entropy is not changing, then it means that I'm sitting at the minimum.
Yeah.
So I have to set ds equal to 0 to identify the equilibrium between these two pieces of my system. But ds equal to 0, or ds is equal to what? Is equal to ds1 divided by dE1. S1 is the entropy of the first system. So I know that S is extensive, right? So S is equal to S1 plus S2. And S1 is a function of E1, V1, and 1. S2 is a function of E2, V2, and 2. At the same time, also E is extensive, is E1 plus E2. And notice that the total E is fixed. This one can fluctuate, that one can fluctuate, but the sum cannot fluctuate, right? Cannot change, it's fixed. Also, the total number of particles cannot change. And even the volume cannot change. I can pretend that a part of my system takes a larger or a smaller volume, but the total volume, V1 plus V2, has to be equal to V, that is fixed. V is equal to V1 plus V2. You see, I'm dealing with 4 variables that are all extensive and whose sum is fixed, given. In particular, the total entropy does not change, the total energy does not change, the total number of particles does not change, the total volume does not change. Only the two pieces can change. Therefore, here in principle, I would have, so ds is what? Is the derivative of S1 with respect to the total energy minus the derivative of S2 with respect to E2, right? Why? Because this is ds1 dE, but E is E1, sorry, just a second, I'm getting confused.
Changes internal energy.
Why D1? This is wrong. It's not correct. Ah, I know why. Okay, now I understand. Since the sum is fixed, right? I can write this, since that sum is fixed. Only one of these two variables is a free variable, right? Therefore, I can write this as ds dE1 plus ds dV1 dV1 plus ds dN1 dN1, right? Because only one of the two variables is a free variable. The sum is given. Now, S is equal to S1 plus S2. Okay? Therefore, this is equal to ds1 dE1 plus ds2 dE1 plus the same thing for the other two terms, right? That is because S is equal to S1 plus S2. So I just inserted it here. Right? But now, you see that here I can change variables. Instead of taking a derivative with respect to E1, I can take it with respect to E2. So E1 is equal to E minus E2. Right? So therefore, taking a derivative with respect to E2 gives you a minus sign. And overall, I get that this is equal to ds dE1 minus ds dE2 dE1 plus ds dV1 minus ds dV2 dV1 plus ds dN1 minus ds1 and ds2 ds2 dN2 dN1. Okay? And to set this equal to 0 means that all these differences have to be equal to 0. So overall, it means that ds1 dE1 should be equal to ds2 dE2. But let's look back at what I wrote here, or here actually. ds dE is 1 over t. So what it means is that 1 over t1 should be equal to 1 over t2. The condition of equilibrium is that the two temperatures are equal. Oh, fantastic, right? It's to be expected, right?
Thermal equilibrium.
What?
In thermal equilibrium, right?
Thermal equilibrium. Condition of equilibrium between these two gases is that the two temperatures are the same.
We can do the same thing there with ds over dE2.
Where? I don't, where?
Instead of ds over dE1, etc.
Well, we can do it with respect to dE2, you will obtain the same thing, right? You just have to change the sign. So, put a minus sign here, and put a minus sign here, and put another minus sign here. So it's equivalent. So this is the first condition. The second condition is going to be, from this term here, P1 over T1 equal to P2 over T2. Right? And the third condition from this one is going to be mu1 over T1 equal to mu2 over T2, which, by the way, since 1 over T1 is equal to 1 over T2, means that the two pressures have to be equal and the two chemical potentials have to be equal. Right?
Equal chemical potential could imply that there is also chemistry, also chemical.
No. I understand what you have in mind. So I'm neglecting the fact that there could be a chemical reaction and therefore blah blah blah. In order to reach equilibrium, in that case, you have to dose the chemical potentials according to stoichiometry, etc., etc. I'm neglecting that because I don't like chemistry. So no, I mean that's interesting. That's part of the game, right? In statistical mechanics, but this is a situation in which you don't have chemical reactions. Okay? So you see how it works. Very easy, very simple. It's intuitive. We all know that in order to have equilibrium, you have to have the same pressure. I mean, if the pressure outside would be 10 bars, right? And here 1, sorry, 10 atmospheres and here 1, the moment you open the window, you get a wind coming in. That you know very well. If the chemical potential would be interesting, you would get the same thing. And if outside is very cold and here is warm, well, we will try this winter. All right. Okay, so now let's see the story of the formula for the entropy for the ideal gas that I promised. And the first time you see something looking like the Boltzmann formula.
Sorry, sir. Just one more thing. This means that the entropy at equilibrium, it imposes that even that there will not only be thermal equilibrium, but there will be some sort of chemical equilibrium.
But this is a trivial chemical equilibrium because there are no chemical reactions, right?
Yes.
If there were chemical reactions, where is the chalk? If there were chemical reactions of this type,
Is that fine?
yeah, so the Feynman diagram is a quantum version of a chemical reaction. Right? So instead of having, it's true actually, I'm not joking. You know, what is, you know, the Feynman, well, you will see what is a Feynman, you don't know what is a Feynman diagram at the moment, probably, but in a Feynman diagram, every object here is a complex function, it's called a green function. In a chemical reaction, every object here is a density, is a real function. So the diagram is the same, but this is the quantum mechanical version because this here you're combining amplitudes, here you're combining probabilities. Okay? The equation here is going to be a propagator in quantum mechanics. So, you know, time ordered exponential minus I here, this thing here is going to get, you're going to get a master equation, dp equal to blah, blah, blah. This is probabilities, these are amplitudes. And you then take absolute value squared and you get the probabilities. So you see, it's connected. It was not a trivial observation, what you just said. Anyway, so if you have a chemical reaction, then, well, you should have, in order to reach chemical equilibrium, you should combine your chemical potentials, etc., in such a way that the rate at which this process happens and the rate at which the opposite happens is the same. So, I mean, essentially, you combine, you reach equilibrium between the products of the reactions and the ingredients of the reaction. Okay? Otherwise, you are always transferring particles from one side to the other. So it's different from this. You have to take into account the various rates and the stoichiometry. I mean, how many of your chlorine ions you need to generate blah, blah, blah. It's a different story. Let's not talk about physics. Sorry, chemistry, please. I mean, it's when I was in university, it was a first year exam, right? And it's the last exam I gave. I mean, I really left it as last because I really didn't like it. Anyway. Okay, ideal gases. Well, we know that for ideal gases, internal energy is CV times T, which is N times R divided by gamma minus 1 times T. What?
The internet is back.
well, the internet is working, but this guy is not connected to the meeting now. General meeting, yeah. I don't know how to do that. So either someone comes here and connects it, or I have no idea. All right, so, and then, well, you know, we will derive it with statistical mechanics, but you know that if you have an ideal gas, well, this is true for the ideal gas, you can also rewrite this as 1/2 F times M K Boltzmann times T, where F is the number of degrees of freedom of your system. This is called the equipartition theorem. And it's valid for classical systems with quadratic Hamiltonians. Okay? Which at most contain a p squared and an x squared, and nothing else. All right, so now let's study again the entropy for the ideal gas. Before we study the entropy for the ideal gas in the case in which what changes is the volume, right? Now let's take a general perspective. So we know that ds is equal to dE over T plus P over T dV minus mu over T dN. Now, you see that since I know what is I can use this formula, essentially the equipartition theorem, to replace the internal energy here as a function of number of particles and temperature. I mean, in a sense, this is true, and not only in a sense, this is true only for ideal gases, right? Or for, well, more in general for quadratic systems, but at the moment we use the version for the ideal gas. So if I do so, I will obtain that this is equal to 1/2 F K Boltzmann. And then I have d n times t over t. Right? I'm using this formula. The only two variables that vary are n and t. So that's why I rewrite things this way. Plus p over v dv minus mu over n, mu over t, p over t, dn. Now, dnt is n dt plus t dn. And therefore this, I can rewrite it as the day in which we will stop using these masks, I will invite you all for dinner. I mean, it's a torture. To teach with this mask is a torture. Anyway, F times N times K Boltzmann dt over T plus N K Boltzmann dV over V plus 1/2 F K Boltzmann minus mu over T dV. Okay? Now, you see that I have a dt over t dv over t v dn there, right? Therefore, if I fix the number of particles, ds at fixed the number of particles is 1/2 f k Boltzmann times n d log of t plus n k Boltzmann d log of v. right? You agree with me?
If you fix what?
Number of particles. And therefore, if I integrate this, I obtain that my entropy as yeah,
What's the difference of the N to?
what d and t.
What's the equivalence?
What is the
D of N T is equal to what?
to n dt to the n plus t the n. D and t is equal to t dn plus n dt.
Yes.
T dn n dt. T t t.
Professor?
Yes.
Backward question. What's this internal energy? I mean,
Of a gas,
of
an ideal gas.
where does F come from?
No, it doesn't come from anything. I just wrote it. Ipse dixit, you know.
And the half?
You know what it means? Ipse dixit, I say it, and therefore it's true. No, it's so we switch to. Okay, you connect, and then I'll switch to the iPad.
Sorry. Professor?
Yes.
If we think about an ideal gas, the number of particles on an ideal gas,
Okay, I can sit down. I'm so happy now. Just a second. Just a second. Okay, ask the question.
don't worry, I think it didn't make sense to me.
So that is something I didn't show. It's as I told you, it's the equipartition theorem that gives you the result. Okay? So, we're in a meeting. Which meeting? 947 1652 897 8679. Join. Passport 8021778. Continue. Okay, join with video. Cancel. Share content. Screen. Start broadcast. And that's it. Okay. So, just a second. All right, so let's continue. Well, so we got to this point, right? ds equal to a constant number of particles equal to 1/2 f times k Boltzmann times n d log t plus n k Boltzmann d log of v, right? So that was our result. Now what I do, and I told you that f comes essentially from the fact that I wrote down there the equipartition theorem. I didn't show it, right? It's just what it is. I told you, for the ideal gas, that is true. Well, I will show it with statistical mechanics. Anyway, now let's take this formula and integrate it. So we integrate.
Oh, so if you fix for one particle, the dn part goes to 0.
Yes.
Just like
If I fix for one particle,
like yeah, or
The number of
the number of
If I fix the number of particles,
the dn is supposed it goes to zero.
yes, that's how I get to that formula, because dn is equal to 0 by fixing the number of particles. So now I integrate, and if I integrate as E, sorry, not E, as T, V, and N is equal to 1/2 F K Boltzmann N log of T plus N K Boltzmann log of V plus a certain function phi of N, which is just a, some initial value of my integrals. That is, I cannot determine from this integration in general, right? It will depend on what I choose as initial point for my integration.
Why is it the function of n?
Well, it certainly has to be a function of n, because this initial point, it is a function of all the variables. In particular, it's going to be a function of n. Right? Because n is the one that is kept fixed. So I'm integrating over v over t, and n is the only variable that is left fixed. If I would integrate also over n, I would get another term that depends on n, right? All right. So now the question now is the following. What is phi of n in general? What should we expect phi of n to be? Well, entropy is an extensive function, right? So extensive means that if I increase the volume and increase the number of particles with scale like volume, the internal energy will scale like volume, etc., etc., etc. Now, when you look at this function here, you see something interesting. Is this first term consistent with the fact that the entropy is extensive?
Yes.
Yes, because it's proportional to n, right? Is this term consistent with extensive entropy? No,
No.
it's not. Because it's n times log of v.
Yeah.
So it doesn't scale like v, but it scales like v log v,
Yes.
right? Therefore, this tells us that in general, in order for the entropy to be extensive, phi of n should contain two terms. Phi of n should have a term that is linear in the number of particles, scales like volume, and then another term that cancels the log v. So I can obtain that by subtracting minus nk Boltzmann log of n. So let me show you how. Someone is smoking or something.
Yeah.
Is it minus minus?
What?
A-n minus minus a.
No, but it's not a minus that minus times minus becomes plus. It's just a minus because I didn't have space. So
So I don't quite get the when you underline both terms.
well, so this is proportional to n, right? And therefore it's extensive. You agree?
Mhm.
This one is proportional to n times log of v. Therefore it's not extensive because it should scale only like n or like v, not like n log n or n log v. It's not extensive. So let's write it like this. Extensive, so if it's extensive, I write a happy face, and this one is not extensive and depressed.
A quick question.
Yes.
I agree with what you said about this quantity, the second term, But I'm also thinking that the log of V is a dimensionless.
You're absolutely right. That's an important point, right? Here I'm completely disregarding the fact that, here, since I'm integrating, I should take some initial value and put it, so therefore this should be ratios of temperatures, ratios of volumes, etc., etc. You're right, what is inside the log should be a dimensionless quantity.
Yeah.
But then when it is a dimensionless quantity, you could take your initial value for the temperature, let's call it T naught and V naught. Now, the point is that you could scale the final volume, right? Leaving the initial one fixed. And then what you would expect is that everything scales like volume itself, not like volume times log of volume. You see what I mean? So therefore, it's correct. There should be something making what is in the logs dimensionless. But it's also correct to say that this scaling is not phi. Should be corrected by the phi of n.
Okay.
Yes?
I didn't get the expression of P of n, why it is.
Of phi of n, why it is like this? Okay, so now I will tell you. So allow me to forget about this story of dimensionless. You're absolutely right. It's a good point, but let me forget about it for a second. Why the phi of n should be like this? Because if I combine these two terms, you see that what I get is 1/2 f k Boltzmann n log t plus, let me write it here, n k Boltzmann log of v over n, right? So I'm combining this with that.
Yeah.
And then plus a times n. And now everything is extensive. There's no n log n anymore, or n log v. Because what sits in the log now is a density, which is an intensive quantity, or a specific volume, call it the way you want. Okay? So therefore, your phi of n has to have this form. Now, so you can also rewrite this in another, if you don't like to use temperature, you can rewrite this in a different form. You can use the fact that T is equal to E over 1/2 f kb times n, right? And therefore, if I substitute this in this formula, I will get that this is equal to 1/2 f n kb log of E over n, so which is the energy per particle, n k Boltzmann log of V over n, plus some b times n, where b, let me write it in green, is equal to a minus 1/2 f k Boltzmann log of 1/2 f k Boltzmann. All right, so this is the general expression I get for the entropy, right? Now I want you to go back to this function phi of n again and think about this function a bit with me, right? So n is much larger than 1. So we know that phi of n has to have this form. I of n has to be a times, where did I write it? A times n minus n kb log n. Now, when I look at this function, right, well, when you see an n log n, what comes to your mind? When n is much larger than 1. Stirling approximation, right? The Stirling approximation tells us that log of n factorial is equal to n log n minus n, right? Now, therefore, this object here for n much larger than 1, for a very large n, you can think of it as minus k Boltzmann log of n factorial plus n times a minus minus k Boltzmann, right?
I want to ask, what is B previously?
What is B is written here. B is equal to this. A minus 1/2 Fk Boltzmann times the log of 1/2 Fk Boltzmann. Okay? All right, so therefore, now I look at this and I substitute it into my expression for the entropy. I get that my entropy is equal to what? To n times A minus K Boltzmann times a function plus a function of temperature, which is that, you know, F times K Boltzmann times log of T, blah, 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 all that stuff, plus n K Boltzmann log of V minus K Boltzmann log of n factorial. And this can be written as n A minus K Boltzmann plus f of t plus K Boltzmann log of V to the power n divided by n factorial. Now,
What is
f of t is some function of temperature. I did not specify it. You see that here you have this 1/2 f K Boltzmann n log t. So it's 1/2 f K Boltzmann log of t. This is 1/2 f K Boltzmann log of t. Now this expression is very interesting, right? Well, first of all, as your colleague noticed, you know, you cannot have something like this sitting in a log. It doesn't make any sense. This volume has to be dimensionless, so it has to be a ratio of two volumes, correct? So, in particular, so it's a dimensionless volume. In particular, let me ask you something. Suppose that I have a certain volume. I'm not able to draw it in 3 dimensions. And then I divide this system into a certain number of cells. Okay? And then, well, the total number of cells I have is the volume divided by the volume of a cell. Let's call it V0. Right? So this is the number of cells. And then I ask myself the following. I have n particles, and I ask myself how many ways do I have to place these n particles in these cells without counting permutations.
Means they are identical.
Yeah, so they are identical particles. N particle, I have n particles, and I put them inside the system without counting permutations.
Is it the same number with n cells?
No.
No.
How many ways?
You want me the number of cells to be called by a different letter. Let's call it Nun. Well, you don't know this letter. It's a Hebrew letter.
Yeah.
Your question is how many ways to put?
How many ways do I have to put these n particles into this strange letter number of cells?
Why don't just use M or something?
What? I want the n cells. It was not good enough for you. I mean, you wanted something else, I give you something else. You know, you wanted something exotic, I give you something exotic. You want me to go back to n cells? I'll go back to n cells. Okay, so how many ways do I have to place n particles in this number of cells without counting permutations?
N cells of n factorial.
N factorial divided by.
So I take these particles and I throw them at random inside this volume, right? And then I don't count permutations.
And one cell can only one particle.
No.
So what is the probability to end up in a cell?
1 over
And
n cells. 1 over the number of
What
cells.
over n?
Anyway, look, let's make it simple. V over, so if you think this way, okay, then this V to the power n divided by n factorial is nothing but the total number of configurations of n particles inside your volume discretized in a certain way. Okay? Otherwise we stay here forever. So if I think in this way and I think that this V should be dimensionless, so what I really meant here is V over a certain V naught to the power n divided by n factorial, right? Then this can be interpreted as the number of configurations of n particles without counting permutations in this volume discretized in this form, right?
Yeah.
So this is the first time we see that the entropy is connected to the number of ways you have to place your particles inside your system, right? The number of arrangements for your particles in the system consistent with the constraints. Well, I don't know if Boltzmann got his idea from this formula. I have no idea. But you see the connection. I mean, it's a germ of a connection between number of configuration, log of a number of configurations, right? And the log of a number of configurations and the entropy. Now, why is this idea important? Because if I have a system, right, and I know that in order to place my particles in this volume, I have a certain number of configurations, v to the n divided by n factorial. Now, if I look at a specific physical system, what is going to be the probability to observe it in one of these configurations?
N over
Over the number of configurations. They are all equally probable. This is going to be a postulate of statistical mechanics. They're all essentially equally probable. And therefore, what you see is that practically the entropy is connected to minus K Boltzmann, right? Let's go back here. If this is the number of configurations, n conf, not n cells, not n part, but n conf, and the probability is equal to 1 over n conf, this formula tells me that the entropy is minus K Boltzmann times log of the probability. You see? So it's a direct connection between what I explained you before and what you see now, between information, probability theory, and entropy. You see that the pieces are slowly going together, right, of this connection. Now we will see it much better in the context of statistical mechanics later, but we see that it seems to be working. All right, so we still have 15 minutes, and then I have to go pick up my kids at school. So what I wanted to do now is to do an exercise to show you how all these various relations for entropy, specific heat, etc., that we found for the ideal gases work in the context of non-ideal gases. Particular non-ideal gases like the ones described by the van der Waals equation of state. Okay? So this way you don't have the impression that all statistical mechanics and thermodynamics is about ideal gases. There are also non-ideal systems. Actually, most systems are practically non-ideal. Now, non-ideal gas. We will start now and finish next time. So the non-ideal gas, for the ideal gas, the energy is, of course, extensive, so it's proportional to the number of particles, and then it's a function of the temperature. Right?
Yes.
Well, for the ideal, non-ideal gas is not going to be a function just of the temperature, but there is another variable that will enter naturally, which is, well, what do you have? You have temperature, number of particles, and volume, right?
Mm-hmm.
Now, from volume, what is the dimensionless quantity that you can construct? The ratio of the volume divided by the number of particles, right? Why? Because the energy has to be extensive, so it cannot be a function of volume only, since I put an n in front. It has to be a function of the ratio of volume divided by number of particles. All right, so now, look at the following. How is the energy in general varying with the volume? Well, for the ideal gas, we know that there is no variation of internal energy with the volume, right? Internal energy depends only on temperature, not on the volume. But for a general system, in which the energy depends also on the density, is going to depend on the volume, of course. So if I compute this derivative, then you see that this is equal to, so what?
Minus P, minus pressure.
well, it's minus P plus something else. So let's think about a situation in which the fixed quantities are temperature, number of particles, and volume, right? And therefore my thermodynamic potential is the Helmholtz free energy, which is E minus Ts. So dE dV is equal to dF dV, constant temperature and number of particles, plus T ds dV. You always have to think about what you're doing, right? The first thing you have to think when you do thermodynamics is, what are the variables that I'm keeping fixed? Then you say, okay, these are the variables. What is the thermodynamic potential? What do I want to compute? Can I use Maxwell relations? You see? It's always, the logic is always the same. So now I use Maxwell relations, right? ds dV is dP dt. And therefore this is equal to what? It's equal to minus P, as you correctly said before, plus T dP dt. Constant volume, number of particles. Now you see something interesting. If the gas is ideal, substitute here the equation of state for the ideal gas. What do you get?
NR.
No. What do you get? If you put in this formula the equation of state for the ideal gas, what do you get?
It could be NR over V, which will still be PV.
I'll give it three possibilities. NR pi 0. What is correct?
0.
0.
Yeah.
You get 0.
Yeah.
Oh, sorry. I don't connect.
You don't what?
I don't connect with the storyline. Where you
Because
get,
you were watching the phone, of
where
course.
you get
that's
minus P and then,
Where do I get minus P? Look, so dE dV, it's a situation in which I'm fixing temperature, volume, and number of particles, right? Therefore, I have to use as my potential the Helmholtz free energy. The Helmholtz free energy is E minus Ts, and therefore E is equal to F plus Ts. So plug in here E equal to F plus Ts, substitute, take the derivatives, and that's what you get, right? Using the Maxwell relations. And now the question is, what is this if I take an ideal gas? The ideal gas is P times V equal to N times R times T. So P is equal to nRT divided by V. You see that if I take a derivative with respect to T and multiply by T, I didn't do anything. Right?
Yeah.
So therefore, minus P times T dPt, dP dt is equal to 0. So for the ideal gas, this is equal to 0, which is consistent, by the way. We know that for the ideal gas, the energy does not depend on the volume. So luckily, we got the correct result. Now, the question is, what happens if the gas is not ideal? Well, we will see it next time, because now it will take me too long. I mean, I was hoping to finish all of this stuff today, but we had some problems. So, but next time, what I would like to do is to show you how to compute this and the variation, for example, of temperature with the volume, right? If you have a free expansion, how is the temperature changing with the volume? And all of this stuff for a gas that is not ideal, but described by the van der Waals equation of state. And that is going to be our last exercise in thermodynamics. After that, we will start with statistical mechanics. Okay? So next time we will do this exercise and we will start with statistical mechanics. All right. Good.